Hello students, in this video I'm going to introduce polar vectors and polar vector functions, and closely related to that, how do we plot polar functions. So as a warm-up, I'd like you to spend a couple of minutes, think about how you would give direction to someone, let's say to go from Fremont High School to Mercado. You would probably say something like, get out of, as you drive out of the parking lot, you turn right, and you probably want to make a U-turn. So you'll be traveling eastbound on Fremont Avenue, and then maybe a couple of miles down, you want to make a left turn on Lawrence, and then you want to head north, and so on and so forth. Now here's a different situation. This turns out to be an actual real city, and let's say you start from point A, which is somewhat to the left of the center of the city, and you want to go to point B, which is on the upper right side of the city. How would you give direction to that person? You probably have to say something like, from point A, you want to travel towards the center of the city. And once you're at the center of the city, you're going to have to pick one of those roads that kind of radially go outwards, and you have to describe one of those roads, whether it's heading northeast, north of northeast, exactly northeast. Somehow you have to describe that particular road that would lead to point B, and then you say, on that road, you want to travel away from the center of the city, and then you'll be heading out maybe half a mile to a mile, and then you'll get to point B. So you notice that the direction you give is going to be quite different from our normal sense of direction, which is going north-south or east-west, turn right, turn left, so on. So the polar graphing or polar notation is similar in the sense that it requires a different way of describing locations. So our plan in this video is to introduce polar coordinates or polar vectors. And then after you view this video, I would like you to practice with polar graphing, which is a worksheet that's in Schoology. And then when you're done with that, then I'd like you to start working on homework 2.6, which is also loaded on Schoology. Think about a vector in polar form as opposed to a rectangular form. In rectangular form, we think about going horizontally however many units, plus or minus, and then we go vertically however many units, plus or minus. The way to think about polar is easiest to think in terms of like a lighthouse. Imagine you are a planted lighthouse. You don't move. All you can do is to rotate your beam to a certain degree, and you can decide how far out do you want to shine your beam. Okay, so you cannot like move right, left, up, down, but all you can do is rotate and decide how far you want to shine your beam. Okay, and that's basically what polar vector says. Okay, you have R, which is kind of the length of your light beam, if you will, and then theta is the angle that you rotate from the positive x-axis. So let's take a look at a few examples of polar graphing. All right. A polar vector has the form of r comma theta that you probably remember from earlier discussions. And what makes a polar function is when the direction theta varies with time, as well as the length of the beam, the length of the vector r also varies with time. When they vary with the parameter t, that would make it a time varying polar vector, which would trace out a function. So here are a few examples. So let's take a look at the first example, which is sine t and t. Okay, don't go to decimals just yet. Let's see if we can sketch it out by hand. So as always, I say when we're not sure what the shape's going to look like, I'm going to build a table. So let's say I build a table with t, and this is my r value, and this is my theta value. Okay, so bear in mind this is r and this is theta. Okay, so let's start with t equals 0. When t is 0, sine of 0, of course, is 0. And theta, since it's equal to t, therefore is also 0. Okay, let's make t equal to pi over 4. Okay, so that's 45 degrees. And sine of 45 degrees is 1 over root 2. And theta, of course, is just equal to t, so theta is going to be equal to pi over 4. Let's go to pi over 2. Sine of pi over 2, we know is 1. And theta, being equal to t, simply is just pi over 2. Okay, and let's keep going. So I have 3 pi over 4. And at 3 pi over 4, sine is going to still be a positive. So it's going to be 1 over root 2. And the angle is now 3 pi over 4. And let's go to pi. Sine of pi is going to be 0. And theta is equal to pi. Okay, let's see if this gives us enough of a clue of what this shape is going to look like. So let's plot this out in the xy plane. But bear in mind, we're not plotting x and y coordinates. We're plotting r and theta. Okay, so when theta is at 0, the length of my vector is 0. Okay, so this one and this one. So that corresponds to a point. I'm going to switch to red color. So this is just a vector of length 0. Okay, so right there. Now theta is going to turn to the next point is pi over 4, which is 45 degrees. So this is my theta. But what is my r? 1 over root 2. Root 2 is roughly 1.4, so 1 divided by 1.4, I don't know, maybe like 0.7-ish. Okay, less than 1. Okay, so the length of the vector is going to be here. So remember, we start out at 0, 0. Okay, and then as theta increases to pi over 2, next point, then my vector length becomes 1. So it's going to be 1 unit. So it's going to be longer than the previous point for sure. And then as theta increases again to 3 pi over 4, so now it's going to be at this angle. And what's the length? Well, it's going to go back to this length. So it's going to shrink back to the same length as 45 degrees. Okay? And then finally at pi, which is this angle now that I'm using my new dotted line, and then the length shrinks back all the way to 0. And you can try some intermediate values in between pi over 4 and pi over 2, and you can evaluate it using a calculator. But what most likely is going to happen is that as the theta increases, my radius, or the length of the vector r, is going to increase up to this point at 45 degrees, and then it's going to keep increasing to 1, and then it's going to decrease, and then it's going to decrease back all the way to 0. So it looks like it's tracing out a circle that is not centered at the origin, rather, but is centered at 0.5, because the height of this circle is 1. Okay, let's take a look at cosine. So once again, let's build a table. T R theta. Start at t equals 0, pi over 4, pi over 2, 3 pi over 4, and then pi. Okay, when t is at 0, r being cosine of 0, cosine 0 is 1, and theta, of course, is just the same value as t. What is cosine of pi over 4? Cosine of pi over 4 happens to be also 1 over root 2. And theta, of course, is just equal to t, pi over 4. Cosine at pi over 2 turns to 0. And t is pi over 2. Sorry, theta is just equal to t, which is pi over 2. Now, as the cosine function turns, remember the cosine function is shaped like this. Once it passes pi over 2, cosine turns negative. So at the angle of 3 pi over 4, cosine is going to turn to minus 1 over root 2. And theta is just equal to 3 pi over 4. And then at pi, cosine of pi would be minus 1. And the angle, theta, is equal to t, which is equal to pi. So let's see if we can plot this curve out. Okay, and I'm going to plot using red. So at t equals 0, r is 1, my angle is 0. So the angle that I am kind of shining my beam is at angle 0, and the length of my beam is 1. So let's say this is 1. As the angle increased to pi over 4, so that is at 45 degrees, the length of my beam is reduced to roughly 0.7, 1 divided by 1.414. So around here somewhere, shorter than 1 to be sure. And then at t equal to pi over 2, the length of my beam is now 0 at the angle of pi over 2. So at the angle of pi over 2, I'm back to 0. And then as the angle increases, okay, to 3 pi over 4, I'm going to have a length of the vector being a negative number, which means I'm going to go back in the opposite direction of the angle. So the angle is in this direction, but because this is a negative length, so that means I'm going the reverse direction, and I'm going the reverse direction at the same distance as 1 over root 2 at 45 degrees. As I keep rotating my angle to pi, I'm going to end up being at negative 1. And since pi is in this direction, negative 1 means I'm going in the opposite direction. So I'm back to this point, 1. So as the angle increases, what I'm tracing out is a curve that looks like this. So it looks like it's another circle. But in this case, the center of the circle is located at x equal to 0.5, y equals 0. So the center of this circle is at 0.5, comma 0. Okay, very similar to the sine, the first function, but the location of the circle is dramatically different. Okay, sine of 2t is going to be much more interesting, and I will give you an explanation, but you don't really need this. If you want to skip this part of the lecture or the video and go to the worksheet, it will be fine. So this time I'm going to build a table also to evaluate this function. But this time I'm going to go in a slower value increment for t. So let's start with a 0. And then I'm going to go to 1/8 of a pi, pi divided by 8. And I'm going to increment by 1/8 of a pi every time. So this is going to be 2/8 times pi. I'm just going to leave it at that. And then 3/8 times pi. And then 4/8 times pi. 5/8 times pi. 6/8 times pi. 7/8 times pi, and finally pi. Okay, so this is r, and this is theta. Okay, so remember r is equal to sine of 2t now. Okay, all right, when t is 0, 0, 0. When t is pi over 8, 2t becomes pi over 4. Sine of pi over 4 is 1 over root 2. And theta is pi over 8. And when t is 2/8 times pi, 2t of that is actually pi over 2. And sine of pi over 2 becomes 1. And this is 2/8 times pi. At 3 pi over 8, this becomes 2 times 2 when you multiply by 2 becomes 3 pi over 4, which has the value of 1 over root 2, and the value of theta is 3 pi over 8. When t is 4/8 times pi, multiply that by 2, that becomes pi, and sine of pi is 0. And this is 4/8 pi. Okay. When t is 5/8 times pi, when you multiply t by 2, this becomes 10/8 times pi. And you remember the sine function, once it passes pi, turns negative, right? So this is going to be negative 1 over root 2. And this is going to be 5/8 pi. And when pi is 6/8, 2t becomes 12/8 pi. So this is going to be at -1. And t is just the same, theta is just the same as t. 7/8 pi, again, multiplied by 2, it becomes 7 pi over 4. And the value is -1 over root 2, 7/8 pi. And then finally at pi, 2 times pi would be 2 pi, and sine of 2 pi is back to 0 again, and this is at pi. So let's see if we can figure out what the shape looks like. Again, let's use red. When t is 0, r is 0, theta is 0. So again, I start right here. When the angle is pi over 8, so it's not 45 degrees, but much less, half of 45 degrees, something like that. My length is roughly 0.7, 1 divided by 1.4. When the angle increases to 2 pi over 8, which is pi over 4, 45 degrees now, my length becomes 1. Okay? And as it increases by another 22.5 degrees, it goes back to 1 over root 2. So this goes back to this point. And then at 4 pi over 8, which is pi over 2, it goes to 0. So I'm going to just be, for these set of values, it looks like it's going to be a curve that looks like this. Now let's figure out the rest. As the angle keeps increasing, so now we are over here, it's going to be a negative length, negative pi over 2, which means it's going to go in the opposite direction. So it's going to go this way at roughly 0.7. And then as it keeps increasing, it's going to go here, which is -1. Again, bear in mind the angle is measured in this direction, but because it's a negative length, so you flip back in the 180 degree from there. And then you keep increasing the angle, so now the angle is pointing in this direction, but because it's a negative length, so you plot, so this becomes 1. This becomes minus 0.7, sorry. And then finally, when you go to pi, it goes back to 0. So it looks like I have something similar also in the fourth quadrant. And if you plot out all the other values, if you keep going, what you find is that you have 2 more of these shapes like either a flower or a propeller of some sort, okay, with 4 petals. So the key about plotting a polar graph is you need to be strategic in terms of picking the values of t so that you have some meaningful number that you can plot on the polar plane, on the xy plane or on the polar plane. Okay. Last thing before we go on, and that is you can eliminate the t such that you actually end up with a polar equation where r is a function of theta. So for example, if you have r is equal to sine of t and theta is equal to t, you can readily convert this into a polar equation because theta is equal to t, so I can just substitute theta into here. So r is equal to sine of theta. And this is a polar equation. Or a polar function. R as a function of theta. What about this one? Similarly, since r is equal to cosine of t and theta is equal to t, I can just plug theta right in here. So r is equal to cosine of theta. All right. And lastly, what about this one? Well, similarly, since r is equal to sine of 2t and theta is equal to t, I can plug theta right in here. Sorry, t. So this becomes r equal to sine of 2 theta. So these, let me bracket them in red, these are all polar functions or polar equations. Okay, so with that, I think you are now ready to work on the worksheet. The worksheet actually steps you through a bit more methodically from the beginning on how to think about polar vectors and polar functions. And when you're done with the worksheet, then feel free to check the answers, which your teacher should be posted in the classroom. And after that, you're ready for the homework. Okay, have fun.